Ladies and gentlemen, boys and girls, Transparent Physics proudly presents an episode of Action Physics. In this episode, we will answer the question as to whether or not Superman kills Batman, specifically a discussion involving the impulse momentum theorem. Welcome to Action Physics. This series is designed to connect my years of teaching high school physics with a passion for the superhero genre, and these lessons are going to try to be designed in a way that you don't need to necessarily know the physics going into it. I'll introduce the basics of what you need as we discuss the assorted topics. So let's dive into our next exciting episode. So this lesson features an episode from the Justice League Unlimited TV series. This was from 2004. Those who know their Justice League from the Cartoon Network series knows that there were 2 seasons of a show called Justice League, and then there were 2 seasons of a show called Justice League Unlimited. I don't know, in my heart, they were just kind of 4 seasons of the same show. Very well done, in my opinion. This is from season 1 of the Justice League Unlimited series, aka season 3. Episode 10, The Dark Heart. In this episode, we're in the New Mexico desert, and the Justice League is being overwhelmed by a horde of fast replicating nanobots who threaten to destroy the Earth. And in order to solve the problem, they make some decisions that have some critical aftershocks in later episodes. In this particular scene, we join the battle as Batman ejects at a high altitude to escape an attack on his jet by robotic marauders. So let's take a quick look.
Batman to all points. I could use some air support, since I can't fly. At all. Now would be good. The spiders are forcing us back.
Okay, that is a great clip from a great episode. And today, Action Physics wants to know, would Batman actually survive being caught in that manner by Superman? And we're going to use the impulse momentum theorem to address this question. And I don't like to play favorites, but the impulse momentum theorem is honestly like one of my favorite equations in introductory physics. I'll show you why. So let's introduce the impulse momentum theorem. This is a variant of Newton's second law, and some people argue that actually the way we write Newton's second law, F equals ma, actually isn't the true way that Newton sort of visualized it, and the impulse momentum theorem is actually closer to the way that Newton was thinking. So if we start with the initial Newton's second law, F equals ma, we can expand F equals ma into F equals m times delta v over delta t. Change in velocity over change in time is the acceleration. And then we're just going to take the time and we're going to move it over. One thing to note, we're going to see this triangle on and off throughout the video. Remember, triangle means delta, which means change in. And anytime you want to solve for delta of any object, you take the final value minus the initial value. So if we move delta t over to the other side, we get force times the time interval equals mass times the change in velocity. So breaking this equation up in a little more detail, we'll take a look at the left side first, and force times the time interval is the impulse. The impulse is the product of the amount of force you exert and the time interval, the amount of time over which you exert that force, which is delta t. And I find this to be a very intuitive measurement. When we talk about applying forces in introductory physics, really, yeah, it's important how much force you apply, but it's also important how long you exert that force for. So I just think this is a really common sense way of thinking about changing the motion of an object. And you have to exert a force over time if you want to change the motion. And where might you have seen the term impulse before? Well, most famously, I think it appears in Star Trek. And Star Trek starships have sort of 2 speeds. There's the warp drive, which everybody knows, but they, at lower speeds, use what's called the impulse drive. on the other side of the equation is mass times change in velocity. And mass times velocity itself is momentum, so we're talking about the change in momentum. And momentum, again, product of mass times velocity, it's similar but not identical to inertia. But if you're comfortable with inertia, you've got at least the scaffolding to understand momentum. And basically momentum deals with objects that are in motion, and we can sort of think of inertia as the tendency of an object to maintain its motion, whether it's in motion or at rest. Objects at rest do not have momentum, but objects at rest do have inertia. And the more momentum you have, the harder it is to stop an object. And the less momentum you have, the easier it is to stop an object. And if we want to change the momentum of an object, we can either change the mass or the velocity. But as far as this particular scenario goes, we're only going to be worried about changing the velocity. We'll assume Batman's mass does not change over the course of the interaction. So looking at this in total, what this equation tells us is how much force is needed in a given period of time to cause a certain change in momentum. And if we assume that an object starts with an initial velocity and needs to come to rest, like in our Batman scenario, the value on the right side of the equation is going to be the same no matter what. You're going to have to lose the momentum you have in order to come to rest. So we can focus on the left side of the equation, which talks about the nature in which we lose that momentum. So let's take a look at two variations of this scenario. In the first scenario, let's imagine that we have a lot of time. And if the right side of the equation is constant, if delta t is very large, then F is going to drop in order to maintain that constant value. So again, if we have a lot of time, the larger the time is, the smaller amount of force is needed. Basically, the argument is the more time you have to change the motion, the less force you have to exert to do so. Sometimes in class, I use the comparison where if you imagine that you're in a parking lot and you see a grocery cart rolling towards your car. If the grocery cart is far away from your car, you're not going to have to really stress yourself. You'll be able to stop the car. All right, it won't be that hard to do at all. But let's take a look at another possible scenario. So the flip side of the coin is, again, we still have to bring the object to rest, let's say. What if our time interval is very short? Well, if our time interval is very short, then the force has to get larger, because again, it has to equate to whatever is on that right side of the equation. So if our time is short, the amount of force needed has to be larger. And so the less time you have, the more force you need to exert. If you are in a parking lot and you see a shopping cart that is just about to hit your car, you're going to have to exert more force in order to bring that cart to rest. And we can expand this and imagine that the cart has some groceries in it too, just to weight the example a little bit more. If it's right next to your car, you're going to have to exert a lot more force to stop it than had you seen it several seconds earlier. So that was a pretty quick introduction to the impulse momentum theorem, but let's just break it out and see what we can do with it in this scenario. So Batman is falling at a certain speed. We're going to have to figure out what that is. And Superman catches him, bringing his vertical velocity to rest to 0 meters per second in, again, we're going to have to figure out what kind of time that is. We're going to simplify this problem, as we often do in introductory physics, and we're just going to focus on Batman's vertical velocity. Now, there is a horizontal velocity component as well. Superman is accelerating him forward towards the camera, and the idea is that while that could complicate things further, we're just going to pretend that Batman is falling straight down and Superman brings him to rest. And then that'll at least give us a window into the physics that we're dealing with. So in order to bring Batman vertically to rest, how much force must Superman exert? So you can see we got a couple things we got to figure out before we can figure out our answer. We're going to need 3 starting clues, 3 starting pieces of information in order to be able to solve for the force. So you can see the impulse momentum theorem there. Force times the time interval equals mass times the change in velocity. The time interval in this problem is going to be the time in which Superman actually physically catches Batman. Not the time that he's carrying him for afterwards, just the time of the catch itself. The mass of the object in question for this problem is the Batman, and the change in velocity is going to be Batman's change in velocity as he is caught. Remember, we're focusing on the vertical velocity only, and delta V is final velocity minus the initial velocity. And we're just going to assume the final velocity is 0. It's a simplification, but it'll help us solve it out. Okay, now that we've seen the clip, let's take a look at it sort of frame by frame and see what else we can figure out. So here's the frame right before Superman catches Batman. Again, they did choose kind of a weird animation perspective to use for this. Superman catching Batman is like super dramatic, but they have it like way in the back of the screen. A little hard to see the actual action, but let's see what we can figure out here. So this, you can see Batman is right here, and this blue and red blur right here is Superman. So in the next frame, Superman's much closer to Batman. Batman actually kind of moves a little bit towards Superman horizontally, but yeah, whatever. And in this frame, we see what I'm going to assume is the first contact between Superman and Batman, and I've identified sort of their vertical height with that green dashed line. The next frame does clearly show that Superman does drop vertically with Batman during the catch, and we'll talk about why that's a good thing. That is a very good thing that Superman does that. And that's it. In the next frame, Superman and Batman start heading toward the camera, and you can see they're still at that same red dashed line, which I'm going to argue means that Superman has completely stopped Batman's vertical velocity. And then from there on out, Superman and Batman just approach the camera at that same vertical height. So as I noted, Superman does give a little bit vertically when he catches Batman. And again, this is a good thing, as we talked about in the impulse momentum theorem. The more time over which that interaction occurs, the less force is required. It's really hard to see exactly how long that catch actually takes in the cartoon. I'm going to estimate that we're at about 0.2 of a second. I think that's maybe a little bit generous, but we'll just use that as a rounded value. And remember that Superman is holding Batman for a lot longer than that afterwards. But I'm just interested in the part where Superman's actually canceling out Batman's vertical velocity. And sometimes in physics we have to do that. We have to narrow down our focus to just the part of the problem where the interaction is occurring, even though there might be more both before and afterwards. Now, in order to solve for the mass, we're going to first talk about weight. Remember, weight and mass are related, but they are not the same thing. Batman, according to my extensive internet research, officially in the comics is said to weigh around 210 pounds. And that does not include his bat suit and utility belt and things like that. I'm going to argue, and again, the internet doesn't seem to agree on this necessarily, but I'm going to say 30 pounds. Let's, for his cape and his belt and his suit, and let's assume his suit is a little bit armored and padded and stuff like that. So his total weight is going to be around 240 pounds. Converting that to mass, and the metric unit of mass, 240 pounds of force is the equivalent of 109 kilograms of mass. So the final piece of the puzzle is velocity, specifically change in velocity, which is final minus initial. We're going to assume that the vertical velocity is 0. Batman's being brought to rest vertically by Superman. And the initial velocity is a term that's known as terminal velocity. And long story short, as you're falling through the air resistance acts up on you. Gravity pulls down on you with a constant force, but air resistance acting on you actually increases the faster you go. So the faster you go, the more air resistance acts on you, until it actually gets to a point where the air resistance acting up on you is equal to your weight acting down. If you remember from Newton's laws, that means your forces are balanced and you're not going to speed up anymore. So good news, if you're falling through the air, after a certain time, you're not going to speed up anymore. Now, your terminal velocity depends on a couple things. And also, side note, when we plug that into the calculations, velocity is going to be negative because it's acting down. Batman, as he's falling in this scene, is sort of head down in kind of a bullet position. I looked up online, that translates to maybe a maximum somewhere around 156 plus or minus miles per hour. That translates to 70 meters per second. Now, realistically, Batman could actually instead be dropping sort of flat belly instead, sort of arms out, legs out. He would actually be dropping more slowly then. So he could have bought himself a little bit of time. I'm not going to question Batman. I mean, he's Batman after all. But he could be making it a little easier on himself if he didn't just dive bomb into the ground. So the only obstacle really left at this point is to get the formula ready to go. I always like to manipulate the formula for the unknown before I plug in values. We're going to be interested in solving the impulse momentum theorem for the force. In order to isolate the force, we're going to divide both sides by delta t. Moving delta t to the other side gets us this relationship. Force is equal to mass times change in velocity. Mass times change in velocity is the change in momentum, divided by the time. And if you take a close look at that, that's really also just Newton's second law. It's F equals ma, because delta v over delta t is the acceleration. Okay, now that we've done all the groundwork, solving is going to be pretty quick. We have our equation, we plug in our values. Quick to note there that this is the final velocity and this is the initial velocity. So final minus initial. If the initial is negative and we're subtracting a negative, that means the change in velocity overall is going to be a positive value. Makes sense because we know that Superman needs to be exerting a force upwards in order to stop Batman. Drum roll, the amount of force is 38,200 kilogram meters per second squared. A kilogram meters per second squared is a Newton, and that's approximately equal to 8,590 pounds of force. So over 4 pounds of force Superman needs to exert in order to bring Batman to rest. Looking at it just in the context of the acceleration is change in velocity over change in time. That works out to around 350 meters per second squared. And sometimes we talk about acceleration in the context of the value of g, just to give us a sense for how it compares to your normal weight. So if we take 350 meters per second squared and take it into g's, that's around 35 g's. So that is a very, very high acceleration. What does that mean in terms of Batman's survivability? So the question is, would 35 plus G's kill Batman? Well, we do have some points of reference for this, courtesy of the United States Air Force. In the 40s and 50s, with the development of jet engines and things like that, people were traveling faster and faster with larger accelerations than we ever had before. And so the Air Force wanted to know if they were going to send people up in these machines, whether it's jet engines or rockets, could people survive that acceleration, both speeding up and slowing down. So they performed a series of tests, and let's go to the time machine.
It fell to the lot of two other Air Force officers, John Paul Stapp and Eli Beating, to demonstrate that men could withstand G-forces as they would be experienced during a rocket launch and re-entry. On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. He suffered no serious or permanent ill effects from the 55G peak deceleration load he took. Beating subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track. Beating went into a state of shock and for a time was considered to be in a critical condition. 5 days later, however, he was back at work with no permanent disability.
Okay, so what does that blast from the past tell us? Let's remember that these tests were conducted on volunteers who were carefully strapped into like a pilot's chair. So the pilot chair supports their entire body. They've got like 5-point harnesses on them. So this is kind of an ideal situation. And even in those circumstances, the volunteers, as you can see from the video, depending on how much acceleration they were experiencing, or could be in pretty bad shape. Colonel John Stapp, who was the first person shown in that video, they said he kind of turned out okay in that clip they saw, but he was a repeated volunteer. Fun fact, he was also a medical doctor too. And I noticed on Wikipedia there was a statement that said over the course of volunteering, he sustained a fracture in his right wrist during runs on 2 separate occasions, broken ribs, fillings from his teeth came out, and bleeding in his retinas so bad that he went blind temporarily. So it was no picnic for a lot of these tests. Okay, so let's put it all together where action physics decides whether or not Superman would kill Batman with this catch. I think we could all agree that ejecting from your bat plane and hitting the ground without a parachute after hitting terminal velocity would be a bad thing. However, an abrupt catch by Superman is only marginally better. Remember, stopping suddenly is stopping suddenly, whether you're hitting the ground or Superman's biceps. And from the cartoon clip, we can see that the change in vertical velocity occurs over a very tiny range. In the Air Force videos, those gentlemen were brought to rest in a little over a second in a lot of instances. Here, I think we can agree that it happens in much less than a second for Batman to be caught by Superman. And calling it a catch maybe is a little generous. We should maybe be thinking about it as a collision instead, at least as far as Batman's perspective goes. So courtesy of those videos of the Air Force testing, we can see that humans have proven capable of surviving even larger accelerations. But that's when they were restrained carefully in sort of ideal test scenarios. Batman, on the other hand, is brought to rest very quickly, and the force is exerted over a relatively small portion of his body, basically wherever Superman grabs him. So that force of contact has to handle all the force for the entire body, and that leaves much of his body unsupported and even more subject to injury during the rapid acceleration. And remember, acceleration can mean speeding up or slowing down. It just means change in velocity. Now, I do have to give Superman some props because as we saw in the cartoon clip, he does drop vertically as he catches Batman, which does increase the time interval. And as we saw in the impulse momentum theorem, increasing the time interval decreases the amount of required force. And there have been instances in the real world where people have survived falling from very, very tall heights out of planes. I think in one instance the person fell through pine branches on the way down. Another person fell into like super deep snow. So anytime you can increase the time of impact, you can decrease the amount of force required and increase your chances of survival. So Superman catching Batman is better than Batman just hitting the New Mexico desert, but maybe not by much. So if we put all this together, action physics decides that, assuming that even the Batsuit might provide some additional protection as well, because it is the Batsuit after all, it is not unreasonable to think that Batman could survive the impact with Superman. Humans have survived larger accelerations, admittedly under ideal circumstances. But I think we can all agree that he would be at risk of suffering severe injuries during the catch and probably wouldn't really be able to continue the fight to save the world against the nanobots. Thank you for watching Action Physics from the Transparent Physics channel. I had a lot of fun bringing this to you today. If you enjoyed it as well, please consider liking the video. If you have anything you want to say about what I talked about in the video, leave it in the comments below. And to be informed the next time I release another action physics lesson, consider subscribing to the channel. And as always, I hope I made things a little clearer for you on this lesson from Transparent Physics.
Where's the atom?
Getting sweaty in here. Is that Batman?